Hey everybody, it's Ripley back again. We're going to talk about geometric sequences in series. Now remember, just a sequence is just a box where you put a bunch of stuff in it. What goes in it? A sub n. And A sub n can be defined all sorts of ways. We can use it as the range of a function whose domain is the positive integers. We have the arithmetic, which is defined recursively by simply adding the same value to each subsequent term to get the next term. Geometric sequence works the same way, only the difference is that just like before, I'm going to let A sub n be defined as, we're going to have the first term is going to be A sub 1. The second term is going to be A sub 2. Third term is going to be A sub 3, A sub n. However, there's a recursive relationship again. Here's the way this works. It's actually simpler. In my brain, I think that geometric sequences and series are far simpler than arithmetic. The formulas are easier to work with. It just makes it easy. It's real easy. A sub 1 is the first term. A sub 2 is simply A sub 1 times r. A sub 3 is A sub 1 times r again, so I get times r squared. In other words, to get from one term to the next, I'm simply multiplying times r every single time, times r. So the next term is going to be A sub 1 times r cubed. And then all the way out to A sub 1 times r. Now let's look close. Remember, this is when n equals 1. You got to keep your bearings on these because they'll screw you up. N equals 2. N equals 3, n equals 4, whoops, not m, n equals 4. You see what it is? A sub 1 times r to the n minus 1. So if you think about this, I mean, look at it. It's real simple. I'm simply multiplying, like before we defined that common term, that common difference is d. This r thing, r is referred to as the common ratio. And that's not sort of flippantly thrown out there. Common ratio. It's called a ratio for a reason. And if you think about it, I mean, look close. If I take A sub r to the n, right, and I divide that by A sub r to the n minus 1, well, what do I always get? I mean, I can just use algebra. The a's disappear, right? And then if I subtract these terms, I simply end up with r. And this is a way that you can prove that series and sequences are actually geometric. I shouldn't say series, that sequences themselves are geometric. So, like, for example, I mean, if I've got 2, and then I've got 8, and I've got 32, and I've got 128, right? And then I've got, what, 5, 12, etc. What's happening here? How am I getting from here to here? I'm multiplying times 4. I'm multiplying times 4, times 4, etc. So this would be, I know that A sub n is equal to 2 times 4 to the n minus 1. But Ripley, is that accurate? Does that always work? Well, think about it. When n equals 1, A sub 1 is equal to 2 times 4 to the 1 minus 1, affectionately known as 0, and anything to the 0 except 0 is 1, and I get my first term. When n equals 2, I always tell my students, just if you're struggling, if you think that this rule is wrong, then check it. You know what I mean? Come up with your own, make sure that your rule actually spits out the sequence that you want. When n equals 2, A sub 2 is equal to 2 times 4 to the 2 minus 1. Well, 2 minus 1 is 1. 4 to the 1 is 4. 2 times 4 is 8. Appears to work. So if I throw something at you like this, 3, 2, ooh, this is looking weird, 4 thirds, 8 ninths, what else? 16 27ths, right? Now, is this arithmetic? Can I come up with a rule? What is A sub n? Well, we know what A sub 1 is, right? A sub 1 is 3. So the question is how do I get from this term to this term? What am I multiplying by? Well, remember, this is when n equals 1. This is when n equals 2. n equals 3, n equals 4. Now, let's play. Remember, if I divide any term by the one immediately before it, I better get r. A sub n divided by a sub n minus 1 always equals r, always equals the common ratio. So if I take the first two terms, I know a sub 2 divided by a sub 1 equals 2 divided by 3. And we can check to see if that's accurate all the way through. We don't actually have to divide all of them because they're fractions and they're awful. So to get from 2 to 4/3, if I multiply by 2/3, does that work? Check. If I get from 4/3 to 8/9, is that multiplying by 2/3? Check, etc., etc. So look, I can define my last term without having to think about it. Look, check it out. Always the first term, which is 3 times what? 2/3 to the n minus 1. Easy peasy. That's awesome. This is always the a sub nth term. Remember that a sub nth term back when we were doing arithmetic sequences? That was the a sub 1 plus n minus 1 times d. Well, this is the geometric sequence equivalence of that. So we got ourselves a piece of information. A sub n equals a sub 1 times r to the n minus 1. Okay? Easy? All right, now, here's where we start to have a little bit of fun. I want to start adding these things up. I want to figure out what S sub n is. Remember, S sub n is equal to A sub 1 plus A sub 2. This is, I guess, another way that we could write this is, I'm going to run out of room, but that, well, I'll write it on the other side. Plus A sub 3 plus dot, 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 plus A sub n, which can also be written as the sum as what? K goes from 1 to n of A sub k. But remember, each one of these guys are defined using this guy right here. See how that works? So really this a sub n right here, I mean, think about it. We could write this as a sub 1 plus a sub 1 times r plus a sub 1 times r squared plus a sub 1 times r cubed plus dot, 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 plus a sub 1 times r to the n minus 1, right? Isn't that true? You got to be smelling what I'm getting ready to do here. Look close. So if I factor out, let's see, do I really want to factor anything out, or is there a more clever trick? Oh, there's such a clever trick. I love it. I almost didn't see my own trick. Watch this. If S sub n equals this guy right here, so S sub n, chink, equals this guy right here, chink. Now watch this. I think you'll like this. Do you agree that R times S sub n is going to equal, all I'm going to do is take R times all of this, and what will I get? I will get A sub 1 times R plus A sub 1 times R squared. I'm just multiplying all of these terms by R, plus A sub 1 times R cubed plus dot, dot, dot. Now watch. I'm going to include two terms here at the end so you can see what I'm getting ready to do. A sub 1 times r to the n minus 1. That's going to be, this term is from the term immediately preceding this, which is a sub 1 times r to the n minus 2, plus a sub 1 times r to the n. See where it comes from? When I multiply this guy times r times r to the n minus 1 produces an r to the n. All right, now here's where it gets fun. Look close. If I subtract these, if I take this guy minus this guy right here, so I'm subtracting all of these terms from these terms, what do you notice happens? Those go away, those go away, those go away, those go away, and all of the terms in between go away. So what I end up with is S sub n minus r S sub n is equal to a1 minus a1 r to the n, right? Nothing to it because all the middle term cancels out. No matter how far out you go, this is always going to be true. So if I want to solve for S sub n, I simply factor out an S sub n, and I end up with 1 minus r. All right, and over here I'm going to dandy this up just a little bit, and I'm going to pull out an a sub 1. That's going to give me a 1 minus r to the n, and this is all over. Well, we're not going to do anything yet, but if I'm going to solve for s sub n, I'm going to divide both sides by 1 minus r, and 1 minus r. Looks like I forgot to close the paren there, so, which implies that s sub n equals a sub 1 times 1 minus r to the n divided by 1 minus r. Now, that's a beautiful equation right there. That tells me that I can sum up a whole bunch of stuff, right? All kinds of stuff in one fell swoop with one equation. Very much like what we had when we did our equations for arithmetic series. All right, you guys, this jittery thing is starting to lag a little too much, so I'm going to back out